Hello everyone, welcome to the first of our Nuclear Masterclass webinars. It's fantastic to see so many of you here. We've just right this second hit over 100 participants so far. I would expect by the end of the hour we should be pushing well up into the thousands. So let's see how we can make that go. It's great to see so many of you here. Welcome to everyone who's joining us as someone who's registered for the Masterclass, as well as anyone from just the wider general public who caught wind of this thing and wanted to come and check out a bit of nuclear physics. My name is Chris Stewart. I used to be a nuclear physicist some 20 years or so ago. I'm now a freelance science communicator. I work with a lot of people at various universities around the country, and I've done a lot of work with the Binding Blocks team over the last several years on anything from producing videos for their programs through to running webinars and masterclasses like this. So it's great to be a part of this event tonight. My job is to make sure everything runs relatively smoothly, to introduce all of our speakers, and to run the question and answer part of tonight's program. We'll get to a bit more of that in a second. A little bit about the masterclass and the webinars themselves. There's a series of 4 webinars that are going to be happening over the next several weeks. Tonight, we're going to be talking about the building blocks of the universe, this stuff that we're all made up of, everything in the universe. Where did it come from? And how can we make more of it in the lab down here on Earth? So we're going to be talking about that tonight. Next week is going to be a bit about nuclear fusion, the stuff that happens in the core of stars, and can we tap into that to make energy down here on Earth? Week 3 is about medical physics and how you can use nuclear properties and nuclear decay in order to both image and treat diseases like cancer. And in the last week, we're going to zoom right into the nucleus itself to figure out what's going on inside there. How do the particles inside the nucleus form the nucleus? What's going on in there, and what are those things made of? So we've got all of that to explore over the next couple of weeks. But for tonight, we're going to be looking at the building blocks of the universe themselves, how the atoms, all the different chemical elements, where did they come from? Before we get into all of that, a few technical details about this evening. It's going to take the form of 2 15-minute presentations by our 2 guest speakers, around which we will have some questions and, we hope, some pretty interesting answers as well. So if you want to ask a question, there's a way that you can do that. Down the bottom of the Zoom screen, you can see a Q&A button. You can access that at any time, throw a question into the Q&A chat, and we will sift through those and we'll do our best to get to as many of them as we possibly can throughout the course of the hour. I can't guarantee we'll get to all of your questions, but we'll do our level best. Down the bottom of the screen, you'll also see a show captions button with a little CC on it. That's the webinar is being transcribed in real time, and so that will help you to follow along if you want some captions, or if you just want to see how well the speaker's words get mangled as we go along. You can turn that one on with that button there. If you have any technical issues, if you get bumped out of the Zoom call at any stage, you can just simply rejoin using the original link that you were sent to join this webinar in the first place. So if you get bumped out, just come back and join us again. And the last thing I should say is that we are being recorded here tonight. And so I'll mention this at the end, but the recording of tonight's webinar will be put up for all to see on the Binding Blocks Nuclear Masterclass website once we've got it all edited together. So without further ado, I think it's time to get on with tonight's presentation. I'd like to introduce our very first speaker for tonight. Our first speaker is Kate Womack. She is a second-year astrophysics PhD student down at the University of Hull. She's specializing in the field of galactic chemical evolution. Now, we tend to think of galaxies as being a very astronomy, large-scale thing, but of course, galaxies, like everything else, are made up of chemicals and elements. And Kate's research is looking at, on an astrophysical level, how do those chemicals and how do they evolve in the context of galaxies? She also does an enormous amount of outreach stuff, including things like tonight's webinar. Kate, welcome. Please, let's kick this thing off with your presentation. Talk to us about your research.
Right, fabulous. I will do that. Awesome. Hi, everyone. As Chris said, my name is Kate. I'm going to be talking to you today about the stellar origins of the chemical elements. So where do all of these elements come from out there in space? And I'm going to start, as all good talks should, with some inspirational quotes from the internet. And so this is the classic "We are made of star stuff" Carl Sagan quote. And there, obviously, it's been co-opted, I guess, by the Facebook inspirational quote pages of the world. It still is entirely true. Everything around us, the elements and the atoms that makes up every object and everything on the earth, started its life in a star. That's me, that's you, that's the laptop I'm talking to you on, the chair that I'm sitting on. Everything started its life in space. And as somebody who, I guess, is in astrophysics rather than in nuclear physics, there's a lot of things that I think about on a day-to-day basis in terms of galaxies and things like that, that can make you feel quite small. But this is the one that really does it for me. The fact that everything around us comes from stars. I have to think about it every day, and it blows my mind every time I do. But let's talk about those things. What are those things, these elements? And so this, as I'm sure you will recognize from school science, is the periodic table. So this places every element, in this case, every solar system element. But it's maybe a little bit different to how you've seen it before. So you can see here that each element is given a color based on the type of thing or type of event that makes it. So you can see up at the top, we've got hydrogen and helium made in the Big Bang. We've got everything sort of in this top half made via explosions. So that's exploding massive stars and exploding white dwarfs. And then everything in this bottom half of the table made by either dying low-mass stars or merging neutron stars. And maybe you can already start to see where I'm going with this talk. I'm going to tell you a little bit about each of these four things. So I'll talk to you about exploding massive stars. So this is an example of one of these. This is the Crab Nebula, which contains within it the Crab Pulsar, which is a remnant of a massive star that exploded and was observed by Chinese astronomers in 1054. And I will talk to you about exploding white dwarfs. This is the X-ray remnant of what we call Tycho's supernova. And this was first observed by Brahe Tycho, hence the name, in 1572. I'll talk to you about dying low-mass stars. In this case, the example we have here is a red giant star, who, as they die and as they evolve, their outer layers expand so far that when this happens to the sun will engulf the whole Earth, and I'll tell you a little bit about that. And I'll talk to you about merging neutron stars and how important their detection was, and that gravitational wave detection in 2017, and what that did for astrophysics, but also for people who are interested in nuclear astrophysics like me. But I will start with the exploding stuff. And we'll start with exploding massive stars, or what I would call a core collapse supernova. And so this tends to happen with stars that have initial masses greater than about 8 times the mass of the sun. So any star that starts its life with a mass 8 times the mass of the sun or greater, this will happen to it. And these stars, because they're so large, have quite violent and quick reactions, which means these stars, at least on a sort of stellar timescale, live quite short lives. We often say that these stars live fast and die young. And when they go through these reactions, it creates this sort of onion shell structure in the inside of the star in terms of the layers of elements that we build up. So through these reactions, we can build up layers of hydrogen, helium, carbon, neon, and so on, until we get to this core of iron. And when the core becomes rich with iron, the star runs out of fuel. It can no longer sustain itself. But you can imagine just how big it's gotten, right? So we've got all these external layers, and that causes a gravitational pressure on the core of the star, which causes it to collapse, hence core collapse supernova. But when stars die, all these elements that they make don't just disappear. They have to go somewhere, right? And so when a star dies, it enriches the galaxy with all of the elements that it's made. So in this case, the gas in the galaxy gets enriched with things like oxygen, magnesium, silicon. These are what we call the alpha elements, and a little bit of iron. And when stars like this die, once they've done that explosion, what remains is either a neutron star or a black hole. And that depends on, again, the initial mass of the star itself. So if it started out somewhere between 8 and 25 times the mass of the sun, it'll become a neutron star. Anything larger than about 25 times the mass of the sun, and that star will eventually become a black hole. But we have two options for explosions. And so our other option are exploding white dwarfs, and we will call these type 1a supernova. Now, these tend to occur in binary systems. So what you will have is you'll have a white dwarf and you'll have its main sequence or red giant companion. Now, what's interesting about white dwarf stars is that these are stars that have reached the end of their lives normally. This is a star that's gone through its full evolution, and a white dwarf is what remains. It's essentially the carbon and oxygen rich core left over from the evolution of the star. But when it's in this binary system with its companion, it sort of gets a second life. So the white dwarf, using its own gravitational pull, takes material from its companion, and it means that nuclear reactions start up again on the surface of the star. And eventually, this white dwarf will reach a critical mass. We call this the Chandrasekhar mass, and it will explode. And this happens at about 1.4 times the mass of the sun. But you can imagine that for this to happen, it takes quite a long time, right? A star has got to go through its full evolution and then steal the material and then explode. So these tend to take much longer to explode than these core collapse supernova that I talked about before. We're talking more than 1 billion years or so for an event like this to happen. But when it does eventually happen, these type 1a supernova make lots of iron group elements. So these are the elements on the periodic table between titanium and zinc. And you can see just with these two events, we can sort of cover most of this top half of the periodic table. But you'll notice I haven't really talked about any elements heavier than iron at this point. And this is because iron is a little bit special when we talk about nuclear physics. And this is because it has something called maximum binding energy, which means it's particularly stable. So it's hard for us to make anything heavier because it doesn't want to take any more protons, it doesn't want to take any more sort of charged nuclei. And so it becomes quite difficult. And so how do we make elements heavier than iron? We absolutely know they exist, they're all there. So what we do is we do something called neutron captures. And neutrons are great because, as the name would suggest, they are a neutral particle. And so if we have a really, really positively charged iron nucleus, and we want to try and add a charged proton, it's going to repel. It's not going to want to do it. It's like trying to stick two north poles of a magnet together. But if we have a positively charged iron nucleus and a neutron, we can sneak the neutron in because it has no charge and make things that are heavier than iron, so we can add mass without adding charge. And this is great. This is how we make all these heavy elements. And it's neutron captures in dying low mass stars and merging neutron stars that allow us to have all of these elements. And so I'll talk a bit about low mass dying stars, and then I'll talk a little bit more about how neutron captures actually work. So low mass dying stars, we would call AGB stars, and this stands for asymptotic giant branch, which is a bit of a mouthful at this time of the day. But essentially what this means is it's a red giant star that is undergoing sort of extra burning. And so when we have a red giant star, the nuclear reactions going on in the center of the star cause this outward pressure. And so we have an outward pressure that causes all of the outer layers to expand. And so when this happens to our own sun, when it becomes a red giant star, those layers will expand all the way to engulf the Earth. But when it becomes an AGB star, when we get even more sort of nuclear reactions, even more mixing, we can expand as far as the whole solar system. So eventually, when the sun becomes an AGB star, it will engulf the whole solar system in its outer layers. But for this, I'm not particularly interested in what its outer layers are doing. Outer layers are primarily hydrogen, whereas the cool nuclear physics is going on deep within the star. And this is where we're making elements like strontium, yttrium, zirconium, barium, all the ions in the periodic table that you don't tend to think about on a daily basis unless you're somebody like me. And we make these elements using something called the S process. So this is a type of neutron capture, which I'll talk about now. But before I do that, I think it's a good idea to show you this. You may have seen this before. This is called the nuclide chart. And so this works a little bit like the periodic table, but for isotopes rather than for elements. And so an isotope of an element an example of this would be carbon-13. So carbon-12 is the isotope of carbon that we're all familiar with, 6 protons, 6 neutrons. If we had carbon-13, that would be 6 protons, 7 neutrons. And so what the nuclide chart does is place isotopes of all of the elements based on how many neutrons they have and how many protons they have. And so it's this concept that I want you to keep in mind as I show you the next slide, which tells you a little bit about how the S process works. So the S process stands for the slow neutron capture process. And so what this means is that if there's some neutrons around in the system, if there's some neutrons around deep within the core of our AGB star, the S process will start to happen. And so you can see here what we've done is we've labeled the stable isotopes as stable, and we've given the unstable or radioactive isotopes a color. And so if we have neutrons around and an isotope is stable, it's not going to decay because it's stable, but it might capture a neutron. And when it does, it makes the next isotope along. So in this case, krypton-83, krypton-84, krypton-85, but krypton-85 is unstable. This decays. Rubidium-85 captures rubidium-86, and so on and so forth. And we slowly and steadily build up heavier and heavier elements by capturing neutrons, hence the slow neutron capture process. But if there's a slow neutron capture process, then presumably there's a rapid one as well, and there is. It's called the R process, as you might be able to guess. And this happens in merging neutron stars. And I'll talk about this in a little bit, but first let's go back and think about what a neutron star actually is. So as I said briefly before, a neutron star is essentially a remnant of a massive star. So after the core collapse supernova, we get this neutron star. And so this means it's packing 1.4 times the mass of the sun into an object which is only 20 kilometers in diameter. Now, I'm based in Hull, so I've done myself a little, so this is a 10-kilometer radius around Hull, which if you're familiar with the area, I guess most of you are probably not, but it gets you sort of to the next town along, which is Beverley. And I encourage you all to do this with the area where you live. Draw yourself a little 10-kilometer radius and see how far you get, because it's really not that far to be packing 1.4 times the mass of the sun into a space that big. But this is what these neutron stars do. And with a neutron star merger, naturally, we have 2 of these, and they're in a binary system. And I'll talk to you a little bit about how this works while I play this movie. So you can see we've got these 2 neutron stars, they're in a binary system, and they interact gravitationally. And it's this gravitational interaction that pulls them closer and closer together. And you can see in this animation, we've got the gravitational waves as well, rippling outwards. And as they spiral closer and closer, eventually they're going to merge. And these mergers are very highly energetic events. And also they have lots of neutrons around. And so high energy and lots of neutrons are the perfect condition for the R process, which is what I'll talk to you a little bit about now. So the R process, as I said, stands for the rapid neutron capture process and needs lots and lots and lots of neutrons. And if we take a look at this little snippet of the nuclear chart we've got here, you can see that we have so many neutrons that actually we go all the way to the end of the nuclear chart nearly, because we have so many that we just capture lots of them. And then once we run out, then those really, really unstable isotopes will start to decay back to something that is stable. And I think you'll hear a little bit more about this later on. And this R process makes things like europium and our precious metals like platinum and gold. But I think before I sort of close my talk, I just wanted to talk a little bit about that gravitational wave detection. So in 2017, gravitational waves were first detected by LIGO, and these gravitational waves came from a neutron star merger. And this was a really important detection, not just to get that first detection of gravitational waves, and not just for people interested in cosmology and other things like that, but also for me, for a nuclear astrophysicist, because this gave us a site which was energetic enough and neutron rich enough for the R process. So that was really great, and just goes to show that big discoveries like this really do go across all disciplines of physics and astrophysics. And so I'll end my talk by showing you once again the periodic table, and you can see here just how much we've covered with just these 4 scenarios. And so we've talked about our exploding massive stars, we've talked about our type 1a supernova, our red giant stars, and our neutron star mergers, and how all of these things can make the chemical elements.
Thank you so much, Kate. Fantastic introduction to where all of our elements are coming from. Now, I just wanted to point out again, everyone is able to throw their questions into the Q&A chat down at the bottom of the window. A couple have come through already. What we're going to do is go through a few questions now, and then we'll go on to the second part of tonight's webinar, and we can come back at the end and mop up any questions that we haven't got to yet. So there's a few coming through already. Kate, I might start off with one that came in earlier on. On your periodic table, where you showed where everything comes from, right, and all the different colors, someone spotted that there are a few that are in gray there, right? Yes. Promethium and technetium aren't made in this way because they're grayed out. Why is that? Why can't we just do that in a star? What's going on?
So technetium and promethium are grayed out because there are no stable isotopes of these elements. So we don't find them on Earth because when we make them in space, they decay. So they decay back to something else. However, what's really interesting about technetium is that if we're doing observations of a star and we see that there's technetium present on the surface of that star, what that means is at the time that we observe it, that star is undergoing active S process. So technetium gets made in the S process, but then because it's unstable, will decay to something else. But if we see it on that star, it means when we've observed it, the S process is happening at that point, which blows my mind. But yeah, that's why, because we have no stable isotopes of these elements.
Right. Okay. So it's not that they're not made at all. It's just that they don't stick around for us to find them later on, and we can only make them later on. Fantastic. Look, why don't we do one more? And then we'll get on to part 2. We'll come up, as I said, and go through a few others later. I like this question. You showed that fabulous video of the merging neutron stars, and that's been such a big thing over the last several years since, as you mentioned, the LIGO collaboration discovered for the first time these gravitational waves, and the first one was from that neutron star merger. So someone has asked, when neutron stars do merge, what do they merge into? What's left behind? You have this enormous explosion of energy, but what do they then make? What is that thing?
So I think it depends on the masses of the 2 neutron stars that you have, the initial masses of the 2 neutron stars that you would have in the first place. The numbers, I don't remember, but when they merge after that event, they will either become another neutron star or a black hole. And that is, to the best of my knowledge, as a non-gravitational wave neutron star expert.
I like to push you out of your comfort zone, so thank you for taking that on, Kate. Look, everyone, please do continue throwing your questions into the Q&A chat. We've got loads of them coming through. We'll be collecting those. But I'd like to move on to part 2. So huge thanks. I'm seeing all of the reactions coming through there. And so do feel free to use the reaction button down the bottom of the Zoom window there. Moving on to part 2, though, the second speaker tonight is a lecturer in physics and an experimental nuclear physicist at the University of York. He's also one of the founding members and one of the core team of the entire binding blocks thing. This is a man who's got more Lego than the rest of us could possibly dream of, because he's the one who started up the whole binding blocks Lego nuclear chart. His research is particularly interested in nuclear reactions that take place in exploding stars, so we're going to pursue that a little bit further now, as well as he's got a bit of a sideline in the research into developing new cancer therapies based on radioactive nuclear isotopes. Please make very, very welcome Dr. Christian Diget. Please, Christian, welcome to tonight's webinar. Over to you.
Thank you so much. Thank you so much, Chris. Thanks for welcoming. All right. So, yes. As you've heard already, my name is Christian Diget. I'm a nuclear physicist. I study nuclear reactions in stars, and I study nuclear reactions here on Earth, and try to see if we can understand more about stars and understand more about how we use the same technologies in healthcare as well. I should perhaps also give the caveat that I'm also Danish. You might find it difficult to pronounce my last name Diget. That's why. It is also slightly linked with my experience with Lego that Chris was mentioning. I must admit a little bit of that. But with that said, let's move to the talk about how we make new exotic elements, both how we do this in exploding stars, but also, and perhaps even more interestingly, how we do this here on Earth. So let's move on to that now. So you will have seen the periodic table. Kate already showed you one version of this, and I'm sure you will have seen periodic tables in the past as well. So this is another chart of the elements that we've got, and you might spot one difference between this, apart from the colors, between this and what Kate showed you. In Kate's version, and let me just move up to here where I'd intended to be. In Kate's version, it stopped at uranium. In this version, we go beyond uranium. And the reason for that is that uranium is the last naturally abundant element on Earth. And the key question that I wanted to ask in this part of the session is, how on Earth do we make the elements that go beyond uranium? And how can we study them? How can we make them here on Earth? How can we find out what their properties are and so on? So that's what we will look at in more detail. But before we do that, just a couple of things in addition to what Kate said about the nuclear physics that underpins all of this. First thing to see is that actually you can see nuclear physics already directly from the periodic table. I've given you here a snapshot of fluorine and magnesium from the periodic table. This is from the periodic table that the Royal Society of Chemistry have published. And if you click on each of the elements, you can see some of their properties. And particularly, what you will see is that fluorine, it has a mass of an elemental mass of almost exactly 19, whereas magnesium does not have this sort of almost integer mass. And the reason for that is that fluorine has exactly 19 of these subatomic particles. Magnesium, of course, doesn't have 24.3 subatomic particles, 24.3 protons or neutrons. The reason for it is that there's more than one type of magnesium. There's more than one isotope, as we call it, of magnesium. And the difference between that is that isotopes is, if you say that one isotope is from a proton and a neutron, for example, you might have a different isotope if you add another neutron onto it, like this. And indeed, that's exactly what we got for magnesium. We've got magnesium 24, we've got magnesium 25, and magnesium 26. But most of it is magnesium 24, and that's why the mass of the element of magnesium is almost, or is closer to 24. So that's the first place I'd say that you actually would see the nuclear physics in this scenario. Now, if we go a little bit deeper into the details, the atom, of course, is built from an electron cloud that surrounds the nucleus. The nucleus has these protons and neutrons inside them. Of course, they're not actually red and blue, but we want to describe them in a way that we can actually see the difference between them. But to get a sense of scale, I think is important. I'm about 1 meter. You can approximate me to about a meter sphere if you want. That's all right. If you scale that down and look in, zoom in by about 5 orders of magnitude, so by a factor of 10, by a factor of 100,000, you get to this to the scale of a human cell. It's about 10 micrometer typically. If you zoom in by another factor of 100,000, you get to the size of the atom. But you need to zoom in by yet another factor of 100,000 roughly in order to get to the size of this nucleus that's made out of protons and neutrons. So that is the kind of scale. It's way off from our normal physical world that we're used to as human beings. So how do we study this? Well, the first thing is just to let you know, this is just pointing back to what Kate was saying about the nuclear chart. We will use this extensively also over the next couple of minutes while I'm talking. But basically, remember, neutrons go horizontally here, protons, so different elements, as you can see, hydrogen, helium, lithium, beryllium, they go vertically in the nuclear chart. And just a little bit of a proof that, yes, I have tried to build the nuclear chart out of Lego, as you can see here. But how do we create them in stars in the first place? This is the neutron-star merger that Kate alluded to. What you can see here is that, for example, that we don't just absorb one neutron at a time in the way that Kate said for the S process. No, we go way out to the edge of stability. For iron, we go about 20 neutrons away. So think about it as absorbing 20 neutrons, and then you might beta decay if you're lucky. And for some of the other isotopes, elements further up, it's actually even more than 20 away. There's some cases where we're more like almost 50 away from the line of stability. The beta decay, what that does is that it takes one of the neutrons in the nucleus and it converts that into a proton. And when it converts that into a proton, it emits, firstly, an electron, because that's how the charge is conserved. Right? We take something that's neutral, we produce the proton that's positively charged, and we emit an electron at relatively high energy from the nucleus. There is also a third particle produced. It's called a neutrino. It's actually an anti-electron neutrino. You won't see that until the very end of your studies, probably. If you're doing A levels, for example, you might see it, or you should see it there. But those are the particles that are actually emitted in the beta decay. This is the beta minus decay, minus because it's a negative electron that's emitted. But when you do this, and this is where it gets interesting, you convert a neutron to a proton. That means you've got another proton in your nucleus. If you've got another proton, your charge is one higher, and you can absorb another electron into your atomic shells of electrons. So this electron cloud now has another particle there, another electron in the atom, and that is what creates the difference. That's what is the difference between the different elements, is really the number of protons or the number of electrons equivalently. So that's one way of creating it, and we can go right up to the element of uranium this way. But what if we want to go further on Earth? So one of the ways we can do that is to do exactly the same as what's done in stars. We can absorb a neutron. As you can see here, you can take, for example, from uranium-238. If we absorb a neutron, we will convert it to uranium-239. We can beta decay, absorb a neutron, beta decay again, and we end up at plutonium, for example. Now, some of these elements, or some of the isotopes, will then emit an alpha particle, and that takes us 2 down in neutron number, 2 down in proton number, because the alpha particle has 2 protons and 2 neutrons together. So that'll take us 2 down in each direction, and it's sort of the diagonal arrow you can see here. But there are ways that you can move through beta decaying nuclei much, much higher up to about a Z value, or a number of protons of 100. That's up to fermion as that element. So that's how the first elements were discovered beyond uranium. You can do that, for example, if you've got a neutron flux from a nuclear reactor. These elements are produced in there all the time. It's just that they're not necessarily extracted. But if you try to extract them, you would find these high line elements. But what if we want to go really far away from uranium? Because this stops at 100. And as you may have remembered from your periodic table, it actually goes up to 118 nowadays. It didn't when I studied, because these later ones were not even discovered at the time. But what you can do is you can take two much heavier isotopes and you can smash them together. So in this case, for example, lead and nickel, if you smash them together, you can make a nucleus called Darmstadtium. And in this case, you get Darmstadtium 271 plus a neutron coming out. That's a nuclear reaction. You can do that if you smash them together with just the right velocities, the right energies. And when you've then produced Darmstadtium, the Darmstadtium might decay via emission of an alpha particle to its daughter nucleus. This would be a hassium isotope. Decay again to its daughter nucleus by emission of an alpha particle. That makes seborgium, and so on. And until it becomes sufficiently stable, you end up getting actually beta decays at the very end. In some cases, you also get fission, in which case we have no idea where we came from. But there's an important aspect about these alpha decays, namely that the alpha decays carry a specific signature of the nucleus that it decays from. So if you know the alpha decay, you know the nucleus. So, and that's because the alpha particle that comes out with a specific energy that's related to the nucleus, and the time it takes for the decay to happen, the half-life or the lifetime, is also unique to each of these isotopes. So what you can see is by measuring the energy and the lifetime of these isotopes, or in this decay chain, you can identify exactly which alpha decays you're seeing, which isotopes you've seen, and therefore you can backtrack all the way up to the start of your chain and figure out, oh, this was the element of 110 in the case of Darmstadtium, and you can count up how many nucleons must that have, and in this case it was 271 in total between protons and neutrons. So you can use this unique fingerprint, and this is indeed how all of these extremely heavy, super heavy elements that we call them have been produced in laboratories. So just to summarize just to give some examples of this, Darmstadtium was discovered in Darmstadt in Germany. Nihonium was discovered in Japan, as you might guess from the label there. Nihon is a Japanese name for Japan. For those of you who don't know Japanese, that's about as much as I know of Japanese. Oganesson is the last element that has been discovered in terms of the number of protons. Oganesson is element 118, and this is what we would think kind of completes the periodic table, or at least we feel that the periodic table is now complete because the whole row is complete, and Oganesson is indeed this probably ideal gas. This is the noble gas element of that row. At least that's what we think. But actually, we don't know much about their chemistry. We only know this from the position that they're likely to be in the periodic table. So with that, thank you for listening. I hope you will enjoy also further on how these elements and isotopes are used in using their radiation to study cancer treatment and many other aspects that you'll see over the coming weeks. So thanks for that.
Thanks so much, Christian. There's just a huge number of questions that are coming through in the Q&A. So please do, everyone, keep them coming through. I thought we'd start with a couple of questions specifically for you. I'm not going to let you off the hook quite so quickly, Christian, and then we'll open up to a general conversation and some questions for both you and Kate in a minute. So thank you very much for that. I find the whole notion of getting right up there into that really heavy part of the periodic table and the chart of the isotopes is just a fascinating place. First thing, question that came through in the chat was, let's suppose that you wanted to study a particular isotope. Let's say, for the sake of an argument, the question asked about uranium-239. Let's take that. It would decay really, really quickly, but if you wanted to, is there any way that you could somehow try to control that and stop it decaying so quickly, or is that something that we have no control over?
You have no control over the time that it takes to, because I can't remember its lifetime, but all of these beta decaying isotopes actually can be studied in the laboratory, because what we need to do is we need to extract them from wherever they're produced and transport them to a detector center section of our laboratories. And the beta decays typically happen on a timescale of milliseconds or slower than that. And actually that is reasonably comfortable from a nuclear physics perspective. We produce them in accelerators, we extract them and so on. So actually that is reasonably comfortable as long as you are not terribly far away from the line of stability. Let's say within, I don't know, 10 or 20 from the line of stability, depending a little bit on where we are. Next generation facilities can actually push further than that as well. But so there have been plenty of studies of uranium-239 as you indicate there. That's actually quite well studied as a nuclear system.
Right, but taking that as just an example, the general idea.
The general idea that, so we can definitely study nuclei that have lifetimes of order milliseconds. Actually, microseconds is also doable. If we push much below nanosecond or picosecond, it starts to get really tricky to do anything before they're gone.
Yeah, that's just starting to get silly at that point, Christian. Listen, next question, and I had written this down myself actually, just on the off chance that we didn't get any questions coming through. I shouldn't have worried, we've got plenty. But you did sort of make a little bit of a throwaway comment at the end there, which is, and now we've filled up the periodic table, right? We've got to Oganesson, which is 118, and we think that might be chemically a Nobel gas, which is, you know, those of you who are familiar with the periodic table, that's the end row. Those are really stable. And so that completes that row and we're done. Except, are we though? Like, couldn't you just keep bashing things together and making bigger and bigger?
Yeah, there's no particular end from that perspective in relation to the nuclear physics of it, right? It's not that Oganesson is particularly special from a nuclear physics perspective in that sense. We are getting into a region where it's getting really tricky because if we go a little bit further, the elements, the isotopes up there might either decay so quickly that they actually don't reach our detectors. That's the timescales that I was talking about. If it's microseconds, it's fine. If it's nanosecond or picosecond, actually, it's really hard to get them to our detectors. And there is a little bit of a cliff we're falling off around there. So it is getting quite tricky. With that said, I mean, I'd be surprised if we didn't detect the next couple of ones within my professional life. And when I say we, I actually mean they. Because I'm doing the
You're not going to find any down the back of your couch.
But it's a little bit interesting to think of how do you even print a periodic table when you get two more of the next row, right? Because it's really annoying.
Oh, that's a technical problem for the chemists to work out.
That's the chemists. Yeah.
That's up to them. That's up to them. And of course, we'll just throw in here. There's the whole issue which we haven't even touched on yet, which is the whole notion of an island of stability. But I'll just throw that one in there, and you can discuss that in the masterclass forums if you want to, Christian. The other one that I wanted to bring up here is, I guess, more of a sort of meta question, really, which is, we find uranium around us in the world, quite literally. We can dig it up out of the rocks. Elements beyond uranium, transuranic elements, we kind of have to make ourselves, and we have to bash things together in the lab in order to do that. Is there a reason to do that beyond the mere curiosity of, like, what can we find? Can we fill out this periodic table? Can we get up to 118 or beyond? Is there stuff that we can do with these transuranic elements? Why are we doing this, Christian?
Yes, so I mean, this touches, from my perspective, it touches particularly on the other strand of my research work in terms of the medical physics. Some of these elements, actually, some of the elements also between lead and uranium, most of those are not naturally occurring, and then the ones beyond uranium as well. So if we can find isotopes within that range where we can produce them at sufficient rates, that's really interesting, because the alpha decay is extremely destructive. and it deposits all of its destruction on a scale, on a length scale that's similar to these biological human cells that I was talking about before. And actually that means that we can potentially destroy cells quite locally. And of course, that carries the potential for cancer treatment if we can be sufficiently targeted. I'll leave the details of that to a future speaker on that topic, but I certainly find it extremely interesting. It's also interesting in that context that we have very little knowledge of what goes on chemically up there, because all of these elements are not naturally abundant. They have really short half-life. We can only produce them in nuclear reactions and then try to do chemistry on them and figure out even just something like our presumed electron configuration, the presumed density or ionization energy, really simple aspects about normal matter that we just take for granted. We know how dense we are and so on. That's not true for these. We just have very little knowledge about how they react chemically. And therefore, actually, these studies include chemical studies of few atoms.
It's amazing how something for a much smaller atom, right down the top layers of the periodic table, something which is so simple as that is clearly a metal, that is clearly a noble gas. Once you get up to these massive, enormous numbers of protons, neutrons, and electrons, that's not so clear anymore. And trying to do both the nuclear physics and the chemistry at the same time for something which is gone like that, it's not an easy thing to do. Listen, Christian, why don't we invite Kate back in? Kate, if you're around, throw your camera and your microphone back on, and let's open up the discussion generally for the last 10 minutes or so. Kate, welcome back. It's nice to have you back with us. I'm going to throw one of the earlier questions to you, but of course, Christian, feel free to weigh in on this one as well. Kate, in your talk, you mentioned the slow and the rapid processes that are forming the various chemical elements and so on. But one of the questions which came through, just a little bit of clarification, we're talking about gaining neutrons.
Yep.
But where are these neutrons coming from? Can you go over that a little bit? Where are they coming from that we can just then absorb those and make new chemical elements?
Okay, so for this, we need to know a little bit about stellar structure and a little bit about nuclear physics. So for the S process, we've got this AGB star, and the structure of the AGB star is such that we've got a shell of hydrogen, and I hope my hand gestures will do this justice, a shell of hydrogen, a shell of helium, and in between that, we have what we call the intershell region, right? Because it's in between the two. And this intershell region is quite carbon rich. And specifically, it's rich in carbon-12. And it's convective. And so what this means is it will pull protons from the hydrogen-rich layer into the intershell. So then we have carbon-12 plus a proton. This makes carbon-13. And then the carbon-13 captures an alpha particle, which comes from the helium-rich region, and this produces oxygen-16 and a neutron. And so it's sort of that combination of the right stellar structure and the right isotopes, and then the subsequent reactions gets us some more oxygen, but also some more neutrons. And then it's within this neutron-rich intershell that those neutron captures can then start to happen.
Right, and so the neutrons and the alpha particles, and by the way, there were a few questions which were coming through in the Q&A, which were just clarifying some of the terminology here. One of the questions was, what's a nucleon? When we say the word nucleon, we mean a neutron or a proton, the things that make up the nucleus. An alpha particle is 2 protons and 2 neutrons stuck together. It's a helium nucleus, right?
Yeah,
but when it's spat out of a nucleus as its own thing, that's a nice little stable lump. We call that an alpha particle. So just to clear that one up. So those are coming from other nuclear reactions, other fusion, or in some cases fission reactions. Those are being spat out and are then available for other reactions to mop up. And you get that transmutation going on.
Precisely.
Right. Okay. Thank you very much for that.
Can I just jump in as well? So it's just an interesting aspect of the nuclear physics that actually the way that these neutrons are produced, fundamentally, we have a lot of protons around. That's what we've got. if you think about the neutron star mergers, what happened was that we had a lot of neutrons around and we absorbed the neutrons. And because we had so many neutrons, they decayed to protons to get closer to stability. And what happens in the proton-rich environment is exactly the opposite, that you absorb the protons and then they have a little bit more proton content than is good for them. And then they beta decay. Now, this is a beta plus decay because they need to get rid of the positive charge of the proton, and they convert that into a neutron. So that's exactly how this carbon-13 is produced. It's effectively the opposite process to the neutron captures that create the neutrons that are then used for neutron captures. So it's kind of it's all within the same family of reactions and decays. It's just sometimes one happens, sometimes the other, and it depends on which type of fuel you've got available.
Right, thank you, Christian. And look, on that kind of ties into a few other questions which have been coming through, and I can tell just by looking at the questions that people are putting into the chat that there's a bit of knowledge out there, but they're connecting things together. So can you help us just connect a few pieces of the puzzle here, right? We've been talking about protons turning into neutrons, or neutrons turning into protons, or this spitting out one of those, and so on. And people know that that's happening within the nucleus, that's part of a nuclear process. But they also know that there are things deep down inside that, and this is perhaps projecting ahead a few weeks to maybe webinar number 4, but let's touch on it. People have heard of quarks, right? That protons and neutrons are made up of even smaller things called quarks. So could one of you just quickly touch on what's happening when a proton turns into a neutron? What's going on?
Yeah, I can touch on that. Firstly, I'll say before I even get to the point of quarks, it's important to remember and note that if you have a free neutron by itself, it can decay to a proton. If you have a free proton, there is no way that it can decay to a neutron, right? Because nature is lazy, and therefore it will always go to where there's least energy, right? It's going to fall down if it can. And the neutron has more energy than the proton. It has more mass, and mass and energy are in some way equivalent. So it's a neutron that decays to a proton, not the opposite. In the nuclear system, it's different, because in the nuclear system, when you put them together, you can have proton-rich environments where you have more energy than their slightly less proton-rich counterparts. So that is the reason why they kind of tend to decay. Now, of course, you need a reason to decay. That's the energy. You also need a process to decay. And the process is what you were touching on, Chris, that in this nucleon, if it's a proton, you've got 3 quarks. If it's a neutron, you've got 3 quarks, but they're different. In the case of the proton, it's what's called we have 2 up quarks and 1 down quark together. If it's a neutron, we have 1 up quark and 2 down quarks, and together they give the charges that we've got. So you can already see now that we've got 1 up quark too many in the proton case. So what we need in order to go from protons to neutrons is that we need to convert 1 of the up quarks to a down quark. And that is the process it's called the weak interaction. And what it does is that it actually changes right down at the quark structure. It's not the global system of the nucleon that's being changed. It's actually the quark inside the nucleus, the nucleon, that's being changed from, in this case, an up quark to a down quark. And that is the process that emits the electron, and in this case it's the positron, the positive electron, and an electron neutrino. Hope that clarifies it a little bit. We'll see much more about it later in the masterclass as well.
Like I said, in a couple of weeks down the track, week 4, I think it is, where we're digging deep right down into the nucleus to talk a bit more about quarks and those sorts of reactions. Really, really quick one from both of you. Questions come through. What's your favorite element? Christian, favorite element? Come on.
It's going to be organesson because it's just fantastic.
Because it's big and new. And you're fickle.
I like new stuff. It's got to be that one.
What about you, Kate? What's your favorite element?
Am I allowed to?
Sure, go for it.
I'm going to say technecium for the reasons I talked about earlier with that active S process detection, but also fluorine because it's where a lot of my research is based, and because it's so low abundance on Earth, but comes from so many different sites in space. So it's really interesting for me.
I'll take a second one then.
Yeah, okay, go on.
Carbon, because it's so hard to make carbon in stars, because you've got to have 3 of these helium nuclei that in some way merges together at the same time, because if you just have 2 of them, they fall apart again. So you've got to have a 3rd one that comes in, and it's really hard to do that in a star.
But carbon's everywhere, Christian. How can it be really hard to make if we've got loads of it?
Well,
That's
that
the
means
thing.
it's got to be a really dense environment, and it's got to be a really hot environment. Otherwise, it's not going to happen. But it does happen. It happens through that sort of 2-stage process. But the intermediate stage, I kid you not, this intermediate stage, it lives for about 10 to the minus 15 seconds. So within those 10 to the minus 15 seconds, you've got that time to absorb another alpha particle.
See, this is what I love about a question like that, is it seems so innocuous. What's your favorite element? And yet people have them, and you people study these things, and you've got reasons for it. Listen, we're almost out of time. We've got time for just one more, and I think there's another sort of meta question here, and it's similar to the previous one, I think, in a way. Someone's asked, should I do physics A level? And Kate, you're not, like, you're second year PhD, right? So you've done a degree and you're now continuing on in your very early stages of your research career. Christian, you're a little bit further down the line. I'm not going to talk about how old you are. But someone who's come along here today obviously has an interest in physics. Should they carry on and do a physics A level? I guess I can figure out what your answer might be, but I'm going to be interested to see why you think that should be the case. Kate, why don't we start with you?
So, I mean, you're absolutely right, Chris. I'm only sort of 5 years or so removed from finishing my A levels, so it's not that far away for me. I would say, to be honest, if you have enough interest in physics to spend your Wednesday evening coming to a masterclass like this, I think you're probably the perfect candidate for the physics A level. At least when I chose my A levels, it was about, I knew they'd be difficult. A levels are hard, everybody will tell you that. So when I chose my A levels, it was about, what am I interested in? What am I going to enjoy hearing about every day and putting loads of work into doing? So I think if you hit those 3 things, and it seems like you probably do, then yes, you should do physics A level.
Thanks, Kate. Christian, a really quick response from you. What do you think?
I would say there's physics in almost everything in life, right? So whenever I look around me, I see physics. And that is because I did physics A levels or equivalent in my case. And then I got sucked into that world of physics. So yeah, it's because there's physics in pretty much everything you see around you.
Thank you both to Kate and to Christian. Look, we've got 125 people joined us here tonight. Not all of you are in a position to carry on and do your physics A level. Some of you are already probably in amongst it, and some of you have already moved on from your A levels. But regardless, you're here on a Wednesday night listening to some nuclear physics, and for that, we thank you. Speaking of thank yous, can you please give it up through your reactions using the reaction button down the bottom of the Zoom window for Christian Diget and Kate Womack? Please give them huge thanks. Look at all the love hearts and the applauds and all the other emoji flowing up the screen there. Thank you so much. It's been a fascinating evening. Listen, I just wanted to point out to all of the masterclass participants, any questions that you didn't get to answer or that we didn't manage to get to, you can always go to the masterclass website. There is the question forum there, and you can contribute your questions there, and our wonderful tutors will be able to get on there and have a bit of a chat to you through the masterclass website there. We are recording this event, and so that's going to be made available on the Nuclear Masterclass website later on this week, maybe early next week, depends how we go. And the link will also be emailed to all of the ticket holders for tonight's event who are not taking part in the masterclass. So if you want to come back and revisit all of this and get it clear in your head once again, then keep an eye out for that one. Thank you so much, everyone, for joining us. We really thank you for turning out on this Wednesday evening. That's brought us to the end. With any luck, we'll see all of you back again next week for Masterclass number 2. Otherwise, thanks for coming along. We'll see you again really soon. Thanks, everybody.